What if I told you PostgreSQL 19 makes your application faster without you changing a single line of code? No new GUCs to set. No application changes. No config tuning. Just upgrade, and the engine itself is faster. Look at this terminal. Toast compression, PGLZ for the last 20 years. PG19 changes the default to LZ4. Less CPU. Better compression. Automatic. Copy from a 50 million row CSV? PG18 scans for escape characters byte by byte. PG19 uses SIMD instructions 16 to 32 bytes at a time. Order by on 100 million integers? PG18 uses quicksort O and log_n. PG19 uses radix sort, effectively linear time. Explain analyze overhead? PG18 calls getTimeOffDate per node. PG19 uses the RDTSC CPU instruction. About 15% less overhead. These are not features you enable. They happen the moment you upgrade. Let me walk you through each one. Here is the plan. 7 performance improvements in 15 slides. LZ4 replaces PGLZ as the default toast compression, the biggest silent change. SIMD accelerated copy from parsing. Radix sort for fixed width keys. Faster row deformation on every select. RDTSC timing for explain analyze. Query-driven visibility map updates. And streaming reads for hash and GIN index vacuum. Stay to slide 11. I will give you the complete benchmark query set so you can measure every one of these on your own cluster. The first and biggest change, LZ4 replaces PGLZ as the default toast compression. PGLZ has been the default since PostgreSQL 8.0. Over 20 years. LZ4 support was added in PG14, but you had to opt in. Most people never changed the default. So for 5 releases, a faster compression algorithm was available but not used. PG19 fixes this. The commit by Euler Tavera, reviewed by Peter Eisentraut, changes default _toast _compression from PGLZ to LZ4. What does this mean? Look at the diagram. PGLZ uses more CPU, that long red bar. LZ4 uses significantly less CPU, that short green bar. And LZ4 typically achieves equal or slightly better compression ratios. Every text column, every JOM column, every bytea column that gets toast, which means any value larger than about 2 kilobytes, now compresses and decompresses faster on both reads and writes. The critical safety detail, existing data is not recompressed. Old PGLZ data stays as PGLZ. New writes use LZ4. You can have both in the same table. The migration is seamless. Which workloads benefit most from the LZ4 default? Anything with large JOM documents, API payloads, configuration objects, audit logs. Large text columns, descriptions, markdown content, log entries. Bytea columns with serialized objects. XML columns with SOAP responses. The key threshold is 2 kilobytes. That is when PostgreSQL starts toasting values. Below that, your data is stored inline and compression does not apply. Above it, you get the LZ4 benefit automatically. Here is a query to check which of your columns use toast. Look at it. Storage X means compressed and out of line, which is the default. And add compression tells you which algorithm is set. Empty string means it uses the cluster default, which on PG19 is now LZ4. If you previously set default _toast _compression equals LZ4 manually, good practice since PG14, then PG19 just makes sure setting the new default. No action needed. Next, copy from gets SIMD accelerated parsing. When you bulk load data via copy from with text or CSV format, PostgreSQL has to scan every byte for special characters, escape characters, delimiters, new lines, quote characters. In PG18, the scanning is byte by byte. One character at a time. PG19 uses SAMD instructions, SSE2 or AVX2 depending on your CPU, to scan 16 or 32 bytes per instruction. Look at the animation. PG18 lights up 1 byte at a time. PG19 processes an entire block in one instruction. The escape scanning loop itself runs 16 to 32 times fewer iterations. The total copy speedup depends on the ratio of parsing time to I/O time. If your bulk load is I/O bound, the parsing improvement helps less. But for CPU bound loads on fast storage, this is significant. One caveat: the SIMD path requires that encoding_embeds_ASCII is false. Standard UTF-8, Latin 1, and ASCII all qualify. Some multibyte Asian encodings like SJIS and Big 5 may not use the fast path. Most deployments benefit automatically. Authors: Nazir Bilalyavuz and Shinya Kato. PG19 adds radix sort for fixed width keys. Comparison-based sorting, quicksort, merge sort has a theoretical lower bound of O, n log n. For 100 million rows, that is roughly 27 comparison passes. You cannot do better with comparisons. Radix sort is not comparison-based. It processes keys byte by byte from most significant to least, using counting sort at each level. For an 8-byte integer, that is 8 passes over the data instead of 27. For fixed-width keys, radix sort is effectively linear O, n times k, where k is the number of bytes in the key. PG19 uses radix sort automatically for in-memory sorts on fixed-width types: integer, big int, small int, float 4, float 8, date, timestamp, timestamps. When does it not apply? Variable length keys, text, varchar, jump, still use comparison-based algorithms. Composite sort keys, order by A, B, also still use quicksort. And external sorts that spill to disk, same as before. The planner chooses radix sort automatically when the key type qualifies and the sort fits in memory. You do not configure anything. Committed by John Naylor, PG19 Final Commit Fest, April 2026. This one is invisible. And that is what makes it important. Every select in PostgreSQL does something called row deformation. It takes the on-disk tuple format, a packed binary blob, and unpacks it into an array of datum values that the executor can work with. This happens for every row in every scan. Sequential scan, index scan, bitmap heap scan, all of them. David Rowley optimized this hot path in PG19. Tighter loops, fewer conditional branches, better CPU cache utilization. You will not see this in explain output. There is no new plan node. The plan is the same. But execution time drops. The effect compounds across millions of rows. A 10 million row sequential scan on a wide table with 20 columns will show a measurable difference. Think of it this way: if the deformation improvement is 2 to 3% faster per row, and you process 50 million rows, that is 2 to 3% off the total execution time. For free. Every time you run explain analyze with timing on, PostgreSQL measures wall clock time at every plan node. Start time, end time, for every node, for every row that passes through. In PG18, this uses getTimeOfDate or clock_getTime, a kernel call. About 50 to 100 nanoseconds per call. 2 calls per node per iteration. On a 50 million row scan through a deep plan, this overhead was measurable, sometimes 15 to 20% of total execution time. PG19 introduces timing_clock_source. On modern x86 CPUs, it auto-selects RDTSC, the read timestamp counter instruction. RDTSC reads the processor's cycle counter directly. About 5 to 10 nanoseconds per call. Roughly 15% less timing overhead in explain analyze. You can check your setting, show timing_clock_source. If it says TSC, you are using the fast path. You can force system for the old behavior if needed. PG_test_timing also benefits. This is an architectural change that connects queries and auto vacuum. The visibility map tracks which heap pages are all visible, meaning every tuple on the page is visible to all transactions. This is critical for index-only scans. If a page is all visible, PostgreSQL does not need to fetch the heap page at all. In PG18 and earlier, only vacuum and copy freeze could set visibility bits. Your queries could read the visibility map but could not update it. PG19 changes this. Regular query table scans can now mark pages as all visible during the scan. Look at the comparison. PG18, a sequential scan reads all pages but marks none. Vacuum has to come back and mark them later. PG19, the sequential scan marks pages as it goes. This means more pages are marked all visible sooner. More index-only scans succeed without heap fetches. And AutoVacuum has less work to do. Author, Melanie Plageman. This builds on the AIO and streaming read infrastructure from PG18. 6 more improvements worth knowing. Each is small individually. Together they are meaningful. Streaming reads for hash index bulk deletion and GIN index vacuuming. Instead of page-by-page I/O, they read ahead in batches using the AIO subsystem from PG18. Notify now only wakes backends that are actually listening for the specified channel. Previously, most backends were woken on every notify. Systems with 100 or more connections and frequent notifications see reduced CPU wakeups. UTF-8 case folding is faster. Lower, upper, the case mapping is cached between calls. TID range scans can be parallelized. Useful for maintenance queries. The AIO worker pool now autosizes with IO_min_workers and IO_max_workers. And adding columns with domain constraints usually avoids a table rewrite now. Here is how you measure these improvements on your own cluster. I promised benchmark queries at slide 11. For Toast, create a table with a join column, insert 500,000 rows with 5 kilobyte payloads. Time the insert on PG18 and PG19. For copy, export a large table to CSV, truncate, then copy from with timing on. Compare wall clock time. For sort, set work_mem high enough to keep the sort in memory, then explain analyze with order by on an integer column. The benchmark checklist, same hardware, same data, same config. Cold cache, restart and drop caches before each run. At least 3 runs, use the median. The improvements compound. Individual gains may be 5 to 15%, but LZ4 plus deformation plus radix sort on a join-heavy analytics query can show 20 to 30% cumulative improvement. What did not get faster? Index builds. B-tree creation is not directly faster. The sort improvements help if the build is sort-dominated, but the I/O phase is unchanged. Planner overhead. Planning time is the same. Complex queries with many joins still take the same time to plan. External sorts. Radix sort is in memory only. If your sort spills to disk, you get merge sort, same as PG18. Variable length key sorts. Text in varchar sorts still use comparison-based algorithms. Connection handling. Still process per connection. No built-in connection pooling. Write amplification. WAL volume is not reduced. These are honest limits. PG19 is faster on execution. It is not faster on everything. Step back for the big picture. PG17 laid data structures. The TID store with adaptive radix trees. Sort improvements. SIMD foundation. PG18 built infrastructure. The asynchronous I/O subsystem. Streaming reads for sequential scans in vacuum. GIN parallel index builds. PG19 harvests. The AIO infrastructure enables streaming reads for hash and GIN index vacuum. The SIMD foundation enables copy acceleration. And the accumulated maturity of LZ4 over 5 releases earns it the default. Each version is faster than the last. And the gains compound. If you are upgrading from PG16 or earlier, you get the cumulative benefit of 3 versions of performance work. 7 improvements. 0 configuration changes needed. LZ4 default toast. Simmed copy parsing. Radix sort on integers and timestamps. Faster row deformation. RDTSC timing. Query-driven visibility map. Streaming reads. Upgrade to PG19. Your application gets faster without changing a single line of code. That is the full walkthrough. 15 slides. LZ4, SAMD, Radix sort, row deformation, RDTSC timing, visibility map, streaming reads. If you run PostgreSQL in production, subscribe. I make practical videos on performance, backups, replication, and upgrades. No fluff. Just the details you need. Comment faster and I will drop the complete benchmark query set in the pinned comment. Hit subscribe. Hit the bell. I will see you in the next one.